Stars are the engines of the cosmos, oases of light permeating the velvety darkness, manufacturing the heavier elements now inside your body and gently warming their orbiting worlds against the frigid cold of empty space. Without them, life as we know it could not exist. Our sun is a G-type star. Those are fairly typical middleweight yellow dwarfs. It was born 4.6 billion years ago, but at that time the universe itself was already 9.1 billion years old. Which means that right now, the universe has existed 3 times longer than our own solar system. Which makes you wonder, what happened before the sun was formed? In those billions upon billions of years that went by, were there different types of stars? Join us today for an exploration of times gone by, as we reconstruct the past and discuss the remarkable, exotic primordial stars that may now be extinct but once roamed the heavens. Alien stars, nothing like our sun. We can get our first glimpse of times gone by looking close to home. Simply by studying the colours of light from the sun, we can determine that its chemical composition is 99% hydrogen and helium. Hydrogen was formed in the Big Bang. That's because it's the simplest element that you can have, being literally just a single proton. Inside the sun, those protons fuse together to form helium, and the energy released is what keeps the lights on. But hydrogen and helium make up 99% of the sun. That other 1% of stuff, which astronomers often confusingly call metals, is everything else in the periodic table. Things like carbon, oxygen, nitrogen, and iron. Curiously, the sun simply isn't hot enough to be producing those heavy elements. It must have been born with these metals from day one. Of course, another example of this is just to look at the planets around the sun here in the solar system. I mean, they clearly aren't pure hydrogen helium either. I mean, I'd say we're pretty metal. So if the Big Bang didn't produce any metals, then where do we get all of these metals from? As stars approach the end of their lives, the core heats up, allowing for the fusion of heavier elements, but generally nothing heavier than iron. Massive stars, which die in spectacular supernova, are particularly good at producing metals, including elements much heavier than iron, even uranium, which we clearly have here on the Earth. What this means is that our sun must have formed from the leftover material of a dead star, a massive behemoth that predated our solar system. You know, I'd like to say that massive stars are kind of like the James Deans of the cosmos. They shine incredibly bright, but live all too short existences. And because of that, they leave an awful lot of hydrogen fuel simply unfused, fuel which can then go on to form new stars. Just like the great actor then, they end their lives with enormous amounts of unfulfilled potential. And so, our much more diminutive sun, forged from the scraps of these cosmic superstars, has enough fuel to happily live a more sedentary existence, but still carry a memory of those progenitors within them, in the form of the metals which now comprise your body. So this reasoning tells us that the sun must be at least a second-generation star, but in fact, given the amount of metals that the sun possesses, it is surely a third-generation star, or even more. We are the leftovers of the leftovers, a double phoenix rising from the ashes. The sun is in fact often referred to as a population 1 star, but the first stars are called population 3. So, what were these earliest of stars like? And what other bizarre stars could have inhabited the cosmos at the dawn of time? Let's explore 3 fascinating possibilities. We'll begin with population 3 stars, stars which we really have to thank for our existence, like a cosmic grandparent. After the Big Bang, 75% of the baryonic matter in the universe was in the form of hydrogen. The other 25% was helium. Now, the Big Bang did create some trace amounts of lithium and beryllium as well, but it's small enough that we can essentially ignore it for what follows. Immediately after the Big Bang, the universe was a hot soup of energy and particles, far too hot for collections of material to stick around and form a star. As the universe expanded, it cooled, and it became more diffuse. Lumps in the primeval cosmic batter, induced by quantum fluctuations, now have the opportunity to locally collapse into gravitationally bound coagulations that will one day go on to form the first stars and galaxies. After around 100 million years, the universe had cooled to about 85 Kelvin. For context, that's about the same temperature that liquid nitrogen boils. It's now finally cool enough for matter to clump together, gas to coalesce, and for population 3 stars to finally make their entrance. But recall that there are no heavy elements yet, so these first stars must have been pristine, essentially pure collections of hydrogen and helium gas. Now, hydrogen is the fuel of nuclear fusion inside of stars, and so these early stars would have been violent in the extreme, unhindered by metals, uncontaminated by pollutants. And there was so much fuel around in such a dense universe that they would have been enormous, weighing in hundreds of times more massive than our sun and shining millions of times brighter. Pristine behemoths of unimaginable energy, yet stars which certainly would have long died by now, and stars which no longer form in our older universe. As a longtime fan of J.R.R. Tolkien's Lord of the Rings fictional universe, I can't help but be reminded of a theme in his work. You see, there's a pattern to his writing, that the universe was born in a pristine, pure state where enchanting, magical phenomena were common, such as elves and miracles. But over time, the purity of the world is contaminated, the lights shine dimmer, and the universe gradually declines in stature until it eventually becomes the one that we know today, one of far fewer wonders. In fact, Tolkien, who was writing in the 1940s, remember, seems to have almost anticipated the existence of population 3 stars that weren't formally proposed until the 1970s. To be more specific, in his legendarium, the first light comes from something called the 2 lamps. These are beacons of beautiful, pure warmth bathing the land. And after that, the 2 trees of, again, enchanting beauty. In the end, the sun and the moon are forged from a single fruit and flower recovered after the destruction of the 2 trees, very much mirroring how the sun indeed formed from the leftover material of population 2 stars before it. But perhaps one key difference is that whilst Tolkien's light of yesteryear are forever lost, there is actually some hope that we might one day gaze upon the light of these primordial population 3 stars. That's because as we look deeper and deeper into space, we essentially look further back in time, thanks to the finite speed of light. And so, look far enough away, and we could perhaps see the light from these magnificent beasts. Indeed, this is one of the goals of the upcoming James Webb Space Telescope, which may well provide our first glimpse of that lost light. What happened to the population 3 stars? How did they meet their end? In the modern universe, stars with masses of 10 to 50 times that of the Sun die in a violent explosion known as a core collapse supernova. Once the nuclear fire in the star's core begins to waver due to depleting fuel, the outward pressure caused by the intense heat diminishes, and gravity takes over, collapsing the star down. We did a video about this recently in the case of the star Betelgeuse that I recommend you check out, but the end product of these supernovae are neutron stars for the lower end of the mass scale, or even a black hole for the higher mass cases, coupled with a violent explosion. So at first glance, this seems like a likely outcome for population 3 stars too, which by simple scaling should leave behind black holes of 20 solar masses or more. However, quantum effects actually start to come into play for these massive beasts. Recall that a star is essentially just a balancing act between outward pressure provided by radiation and inward pressure provided by gravity. And normally those two are equal and opposite to each other, else the star would either implode or explode. And that balance is naturally found in the star through gradual compression relaxation in the interior. But for population 3 stars, they are so energetic that a bizarre quantum effect can come into play and interrupt that delicate balance. As stars get older, they compress as a result of manufacturing denser elements in their interiors, which in turn heats up the core, leading to an increase in the overall power output. At a certain point, the energy being produced by population 3 stars is so high that a huge amount of gamma rays, the most energetic form of radiation, start to be produced. In fact, gamma rays are so energetic that they can play some weird tricks. As they collide with other particles, even sometimes including themselves, they can transform from energy into mass via E equals mc squared. Now even gamma rays don't have enough energy to make much mass though, just the lightest stuff imaginable. An electron and a positron, a matter-antimatter pair. The moment this happens, it's like kicking the wind out of the sail. The outward radiation pressure that these gamma rays once provided suddenly goes away as the gamma rays transform into mass. Now, small decreases in outward pressure are okay. The star has time to gently compress and reach a new equilibrium. But every readjustment made just makes the interior more chaotic, more tumultuous, and that leads to further greater changes in the energy output of the star. Eventually, an episode of particularly pronounced gamma ray emission occurs, which then goes on to form a sea of positron-electron pairs. The star might have been able to take a few punches up to now, but its back's up against the ropes, and this final blow is just too much. The outward pressure suddenly sinks, and the star just falls in like a boxer to the 10 count. The momentum it gains during this infall is just too much to resist with gentle adjustments, leading to a sharp increase in the core pressure. That pressure turns the nuclear fire in the center up to 11, and in the space of just a few seconds, runaway nuclear fusion releases more energy than the gravitational binding energy of the entire star. An immense explosion occurs, known as a pair instability supernova. So violent is this final flourish that the star literally rips itself apart all the way from the center. There's no neutron star left behind, no black hole. It just completely explodes. Now, in a way, these supernovae are the most selfless of cosmic events, for in their final moments, they sacrifice themselves, throwing out their entire enriched guts across the cosmos, made available to form the maximum number of new stars. Nothing is wasted in black holes. It's astonishing to think that many of the heavy elements in your body were likely forged in this unimaginable environment. Such supernovae are predicted to be very rare these days. After all, stars massive enough to do this are largely gone by now. But in rare cases, such massive stars could still form, and indeed there are several supernovae which have been observed that are potentially energetic enough that they could have indeed been a pair instability nova. However, a basic prediction for these events is that no black hole is left behind. They completely explode. And that, in turn, means that the most massive black hole that can directly form from a star would be about 15 solar masses. Remarkably, gravitational wave measurements made by LIGO have recently found black holes in the 20 to 30 solar mass range. These could have plausibly formed from mergers between smaller black holes, but perhaps there is some way that population 3 stars can form black holes after all, something we don't understand yet. And that has triggered renewed interest in the life cycle of these enigmatic objects. You know, this is why I love astronomy. With each discovery, new surprises meet us, challenging us to dust off our old theories and invite fresh new ideas. What an exciting time to study the universe. Population 3 stars are hundreds of times heavier than our Sun, and dozens of times larger in size. But as impressive as these objects might seem, they pale into insignificance compared to an exotic star hypothesized to exist at the dawn of the universe, the dark star. Recall that stars are really just a balancing act between outward thermal pressure and inward gravitational pressure. Stars form from large clouds of hydrogen gas, which gradually collapse until their densities are so high that nuclear fusion is triggered, which then resists further collapse. But dark stars circumvent that process. Long before this cloud has a chance to collapse to a point where nuclear fusion would take hold, a different outward pressure emerges from an exotic effect which resists further collapse. The suggested mechanism for this outward pressure comes from dark matter. Dark matter is extremely abundant, making up 85% of the matter in our universe. What dark matter is, we don't precisely know, but we do know that it is something which doesn't like to interact with ordinary baryonic matter except through gravity. It's very simply invisible stuff, which is why it's so hard to study. One of the most promising candidates for what dark matter is made out of are called WIMPs, weakly interacting massive particles. These particles would barely interact with the ordinary baryonic matter that you and I are made out of. That's why we don't see them. But they would be their own antiparticle. That means that when two of them come together, they would annihilate into pure energy. And it's exactly through that mechanism that they could provide the energy needed to birth dark stars. Remember that in the early universe, everything is much denser and hotter than today. Dark matter is usually very diffuse, like cosmic fluff spanning many light years across. Because it doesn't interact with ordinary matter very much, it's very difficult to get dark matter to collapse down like normal baryonic matter does. On that basis, it seems very unlikely that a star could form from dark matter. But because the universe is intrinsically denser in these early days, there's a lot more of it around in any given volume back then. So the idea is that as a giant cloud of gas starts to contract in an attempt to form a normal star, enough dark matter can get localized in this bubble that self-annihilation becomes important. And the energy produced by these annihilations between dark matter particles is enough to resist further gravitational collapse. So you end up with a giant, spherical, and luminous region in equilibrium, which essentially defines a star. But these stars would be truly bizarre. Because dark matter annihilation halts the collapse much earlier than baryonic fusion would, the star is gigantic, up to 20 astronomical units in diameter. For context, that would mean that the star would engulf the orbit of Saturn and have a volume 10 billion times larger than that of the Sun. Despite its spectacular size, the energy output doesn't scale quite as dramatically, and so its surface, if you can even really call it that, could be as cool as a few thousand Kelvin. That low-end estimate is about the same temperature as the coolest red dwarfs in the modern universe, and so the dark star may not even actually emit much visible light. Dark by name, dark by nature. Over time, the dark matter in this region will deplete, so much so that gravitational contraction will resume and eventually go on to form a population 3 star in the center. But the dark star phase could last for tens of millions of years, long enough that we have a chance of catching it in the act. These objects would be very difficult for us to observationally confirm if they are limited to the very early universe, largely because they'd be so far away. Nevertheless, there is some hope of finding them with next-generation gamma-ray telescopes which could pick up the annihilation photons. For now then, dark stars remain a hypothetical but captivating object. And so concludes our exploration of the first stars. The early universe was a dense, hot soup devoid of stars like our Sun or planets like our Earth. But it was also a time of awakening, when the first stars were born, objects of pure, pristine composition, magnificent stars shining brighter than any of those of today. Within these stars, different physical principles ruled, leading to bizarre objects and incredibly violent novae. But from the ashes of that era, the seeds were planted for what would eventually blossom into systems like our own. It's amazing to think that Even in the most optimistic view of life, there was almost certainly no sentient life forms around to witness these early days. If there had been, and somehow they survived until now, they might well look back with a hint of sadness and remorse that those stars will never again rule, that the cosmos will never again shine the way it did in those pristine years. The universe is compelled to inexorably increase in entropy over time. Once pure in composition, pristine, it is now riddled with metallic contaminants, polluted ever more over time. And yet it is from those pollutants from which we formed. Without that stellar waste, none of us would be here. And so whilst we might well wonder what those early pristine days were like, we have to accept that we are made from muck. We are the universe's waste products, its pollutants, its contaminants, its trash. And that is glorious. Because you see, my friends, there's some treasure in that trash.